Hello everyone, I am Varun and I represent the Media Intelligence team at Microsoft, and we work on video-related AI features for the team's product. Today I will discuss our challenge on video quality enhancement aimed specifically at the domain of video conferencing. This presentation will be followed by two of the top submissions that we received. First, let's look at the motivation. Here are some videos that we see on Teams, and I would say that for every video that has good uniform lighting with minimal sensor noise, we get at least four that have suboptimal lighting or poor quality camera or calibration issues. And this often leads to over or underexposed images, color shifts, and noticeable video noise and artifacts. The current solution that we have in production is a global luma and chroma correction model, where a CNN that works on downsampled 96p images predicts a 1D lookup table every 1 second. We fit this 1D LUT to simple polynomials, which are applied at full resolution for each frame. This is very fast since the CNN has a per frame latency of only 1 millisecond on CPU, and the application only takes 0.3 millisecond at 720p. However, since this mapping is global, we give more importance to foreground colors, and this may lead to improper exposure of or color shifts in the background as seen in the videos. Moreover, it does not tackle denoising at all, and in fact, it may make noise more noticeable when it boosts Luma. As an extension, we also explored local correction model that aims to light subjects in a canonical way and corrects for oblique light. We achieve this by a CNN-based guided filtering approach that does detailed transfer from high-res input image to the predicted image without needing to do inference at the native resolution. Hence, this approach is also lightweight, and we can do 8 millisecond CPU inference for a 720p frame. However, as we see in this videos, one side effect of simulating diffuse light in front of people is the reduction of local contrast, which often serves as a proxy to convey depth in 2D images. Ultimately, this makes people appear dull in some cases. To validate our intuition, we conducted a large P910 subjective study totaling 350,000 pairwise comparisons. Then to transform this into a ranking order, we use the Bradley-Terry model that gives us a real valued score P that maximizes the log likelihood of the observed pairwise voting. We see that people prefer global correction much more than local correction. And when we asked what factors affect their choice, people cite brightness as the most important metric. This makes sense because our local correction model often reduces Luma in overexposed regions. We further see that the strength of Luma correction is proportional to the score, which is further proof that people do not really care about optimal lighting, they just want the brightest scenes. And since global correction is ranked the highest of all methods that we have, we supply this as a baseline solution to the teams. Now the core problems remain: A, to understand what people prefer and construct a differentiable video quality assessment metric. For this, I will show how our VQA model works in later slides. And B, train a video quality enhancement model that optimizes this metric. And this brings us to the problem statement for this challenge. So we asked teams to design a VQE model that improves the appearance of videos in terms of luma and chroma, while also tackling the problem of denoising. The goal was to have a computationally efficient solution that can be offloaded to NPU for CoreML inference. So we established a qualifying criteria of UINT8 or FP16 models with at most 20 gigamax per frame. And we expect such a model to have a per frame processing time of around 5 milliseconds on the newer M4 Pro. Now let's look at the datasets that we provided. First is the pair data for fully supervised learning as shown on the top of the image. We will see how this data is rendered in the next slide. There are a total of 2,000 videos in the subset, each 5-second long and encoded at exactly 30 FPS. Next, we have 13,000 unlabeled real videos. These are 10 seconds long and encoded at an expected frame rate of 19 FPS. The teams were encouraged to use the provided differentiable VQA model to perform self-supervised learning using this data. Of these, we selected 300 videos where the raters voted strongly in favor of the baseline solution with a mean opinion score of 3.58 in the favor of target. And these were provided as a paired subset of the real data. Finally, here is our synthetics pipeline. We use a physically based path tracer and our own photorealistic assets in Blender to render these scenes. On the right, you can see how the source image has lighting only from the Ntire environment. For the target, we added two light sources to simulate a studio lighting setup. The first is a key light, which may introduce shadows on the face. And to correct for this, we add a fill light, which is more diffuse so that it does not cast any additional shadows. These two lights are rigidly mounted with respect to the face. And to control the total incident light on the face, we completely turn off the background HDRI light for the target. Finally, to ensure this data generalizes well in the wild, we distort the source image by adding out of focus blur, channel independent Gaussian noise, and finally some sensor noise sampled from a Poisson distribution. And P910 done on these videos shows a MOS of 4.06, indicating that these make a good target. Okay, now on to the VQA model that we provided. We give a pre-trained Siamese model that, given a pair of videos x1 and x2, predicts the probability of x1 being preferred over x2 in a P910 study. We noticed that Dover is a good candidate for an assessment model but performs poorly on our domain of data. Hence, to construct this model, we use a pre-trained Dover technical branch, which is based on a video Swin transformer and captures low-level visual distortions such as noise, flicker, video coding artifacts, and frame freezes. But for better understanding of semantics in our own data, we use a low-res aesthetic CNN embedder pre-trained on our data. The model also outputs 11 auxiliary scores for each input that correspond to factors such as color harmonization, face liveliness, image composition, etc. And these are supervised with metrics obtained from publicly available Apple Vision APIs. The model was trained on 22,000 videos and 11 different enhancement models. And ground truth labels here were collected by human raters, totaling more than 300,000 side-by-side video comparisons. As for evaluating this model, we notice that the model has some correlation with Dover scores, but it adapts to our data domain better. And this can be seen by a very low absolute error of only 0.07 for the task of predicting MOS in the range of 0 to 1. Here is a snippet of our subjective study. Each task has 10 videos, which are played in full screen. After watching each video, the raters are asked to provide a MOS rating on the scale of 1 to 5. They're also asked if they made the choice based on colors, brightness, or skin tone. I should also mention that there is an onboarding section where the raters are asked to calibrate their displays and pass some basic visual acuity checks. This framework has a throughput of around 200,000 votes per week. As for participation, we had 95 registered users and received 10 complete submissions. For each submission, we received 3,000 corrected real videos, and we conducted 270,000 side-by-side comparisons to get these results. We see here that 7 of the 10 teams came up with solutions that were better than the baseline, and all of them rated better than the input videos. All of them did inference at full resolution to maintain sharpness. One trend that was very clear is that lookup tables are the key to reducing MAC counts. And there are only 3 submissions that do not use LUTs, and all 3 of them did not meet the qualifying MAC criteria. Looking at more detailed metrics, we see that relative ranking of different methods remains roughly similar when ranked by color, brightness, and skin tone compared to overall performance. Of these 3 factors, brightness has the highest correlation with overall scores, followed by color. Finally, we look at some videos. Notice that the 2 videos in the first row are the same input video, followed by the baseline solution and then the top 5 submissions. We can see that all 5 submissions do significant denoising compared to the baseline solution, which helps them rank better. The top 4 winners also do sharpening, which is evident from the eyes on the right video. We also see that the top 3 submissions do modest color correction compared to the heavy correction done by number 4. Thank you, and please check out our webpage by scanning the QR code above to access our datasets and the models.